Hello and welcome to another video. This one was inspired by a question from Ash Nakamura, who was asking basically about the MART scheme here, and I think it's well worth talking about because I think there's a mistake in the MART scheme, and I very rarely claim that unless I've sort of had a good look at it and thought it just doesn't make sense. So let's see if we're right. Firstly, this question, I didn't like it. I don't think I would have got it right in exam conditions at all. I made a blunder. I'll tell you my blunder. I read the question as if it was saying, is this always a cube number? Yeah, and I thought, well, clearly it's got k plus 1 as a factor because k is minus 1 makes it 0. And then I thought, well, as that's not equal to k plus 1 cubed, you know, like quite clearly isn't equal to that. I was like, oh, well, it's not a cube number. But obviously, and another commenter pointed this out to me, and it's like, yeah, you're absolutely right. That what I'm showing there is whether this is always a cube number, regardless of the value of k. In other words, I'm showing that for all k cubed, well, I was showing that it's not possible that for all k cubed plus 2k squared plus 2k plus 1 is a cube. And that's not what the question is asking. The question is saying, does there exist a k such that k cubed plus 2k squared plus 2k plus 1 is a cube? And that's a very different question. Now, don't get me wrong, I love their first explanation. I think it's a very clear explanation. It's basically like, for any value of k, this has to lie between two cubes, because obviously k cubed is less than this, but the very next cube number, which is k plus 1 cubed, well, that equals something which is clearly greater than this, because remember, we're only dealing with positive integers here. As a result of that, you can say that, you know, there's no way this can be a cube number since it lies always between two cube numbers for all values of k, yeah? And so doesn't exist a positive integer where that's true. Now, that's a very good argument, and I like that. But the question was, what about this alternative approach? And I admit that I would probably have, like, not that I did it, but the alternative approach makes a lot of sense. And essentially it's a proof by contradiction. So let's try and make some sense out of it, and let's correct the offending line, which I believe is incorrect. Okay, so the alternative approach is to say, okay, so basically it's a proof by contradiction. Assume there exists, okay, such that k cubed plus 2k squared plus 2k plus 1 equals n cubed, where k and n are members of the positive integers. Yeah, and cool. Yeah, we're saying that's the case because then this is clearly a cube number. Yeah, so we're saying, okay, let's assume that this is a cube number. This is a lovely way of basically assuming this is a cube number. And then they do the kind of things, and actually they use the result from much earlier on in the question, but it's perfectly possible, and you should be aware of how to factorize the difference of two cubes. Yeah, it's like the difference of two squares, but it's the difference of two cubes. You can see that if n was k, this would be 0, and so by factor theorem, n minus k is a factor. Yeah. And then what we can do is we can do that kind of division by inspection approach to work out what we need to multiply it by. Well, we need an n squared here to make the n cubed. That would give me a minus kn squared, and sometimes this is easier to see in a grid, but I strongly encourage you to get really super quick at factorising because we do it all the time in these extension papers. We're going to get minus n squared k, so we're going to need a plus n squared k to get rid of that, which means this needs to be nk. Yeah? Now that gives me a minus nk squared, and so I'm going to need a k squared here to make a plus nk squared to get rid of that, and then these two cancel, and finally we're given minus k cubed. So we've factorised it correctly. So we've got n squared plus nk plus k squared. What it means here in the MART scheme is that in part 1 you derived a general result for factorising difference of two cubes, I think, and so you could have used that general result. Yeah. Okay, so we've shown this is true. Now, so we've assumed that this is true, and we're going to try and derive a contradiction, because this is a proof by contradiction. How are we going to achieve that? Well, note both this line, but also this very first line here. Can you see here that k must be smaller than n, because they're both positive integers, and we're cubing them both, but with k we're adding some stuff on, and then it equals the cube of n. So clearly k must be less than n, or n is bigger than k. You can also see it from this line. The left-hand side is supposed to be a positive integer. Well, that means that n must be bigger than k, because otherwise we're going to have 0, or we're going to have a negative number, so n must be bigger than k. So we can say, clearly, n is greater than k. Now before I go any further actually, can I just jump in here and look at this result here? We're saying that 2k squared plus 2k plus 1 equals these two multiplied together, and that's the case if this first statement holds, which we're going to try and show isn't true. But what we can deduce from this, we can deduce that n squared plus nk plus k squared, well, that must be less than or equal to 2k squared plus 2k plus 1. And it will be equal to 2k squared plus 2k plus 1 when this is equal to 1. In other words, when n equals k plus 1. Yeah, if n is k plus 1 here, then you're going to get 1 in that bracket, and therefore this equals this, yeah? That's where the equality case holds. Now, I just wanted to point out, because I'm going to come up with two contradictions, and I think it's just a bit clearer what's going on than their argument, or at least it is in my mind, but that's just the way I understand it. I'm not criticising them. I'm definitely not criticising the people who write the MAC questions or any of the extension paper questions, because it's really hard. I just think they've made a slight slip. I disagree with this statement here. And maybe it's me, but I cannot see how they deduce that. So I'm going to show you what I can deduce. I think they've got the inequality sign all the way around. So, okay, clearly n is greater than k, and they're both positive integers, and if this is strictly greater than k, what we can do in the next line is point out that n must be greater or equal to k plus 1. Yeah, that must be the case, mustn't it? If these are both whole numbers, and n is bigger than k, then what we can say is n is definitely bigger than or equal to k plus 1. So think of the case where they're closest, n is 6, k is 5, well then 6 is equal to 5 plus 1, isn't it? Yeah, clearly that's the case, yeah? Now what can we use this for? Well, straight away I could multiply both sides by k. I'm going to show you exactly what I'm doing here, because I think I've skipped a few steps here. That gives me nk is greater than or equal to k squared plus k, yeah? But I'm also going to use this one in another way. I'm going to square both sides, which is fine because I'm dealing with positive amounts on both sides. I can square both sides, yeah, and that's going to give me, and I'll write this next to it, n squared is greater than or equal to k plus 1 squared, but that means that n squared is greater than or equal to k squared plus 2k plus 1, yeah? And now, generally speaking in inequalities, be careful combining inequalities, but definitely if a is greater or equal to b, and c is greater or equal to d, then you're absolutely allowed to add them here. Don't subtract, that's a different story. A plus c is greater than or equal to b plus d. Look carefully at the rules for inequalities before going into any of these extension papers. They're not as simple as you think. That's a whole nother video in itself when you can't subtract inequalities. I might quickly show you, you know, a justification for why you can't subtract. Let me see if I can think of one just off the top of my head. Minus 2 is, let's say minus 2 is greater than or equal to minus 3. But 4 is greater than or equal to 2. Okay, if I subtract them, minus 2 minus 4, I get minus 6 is greater than or equal to, now I'll subtract this one, minus 3 minus 2 minus 5. Is minus 6 greater than or equal to minus 5? No, that's wrong. You can't subtract inequalities, but you can add them when you've got inequalities facing the right way round. Just to show it works here, 2 is greater than or equal to minus 1, yeah. So basically, yeah, be careful with inequalities. They're not as simple as you think. Yeah, they really aren't. They're not as simple as I think. I have to be ever so careful when working with inequalities. Sorry, gone off on a bit of a tangent there, but I just want to explain I've got two inequalities now, this one and this one, and I can add them, giving me n squared plus nk is greater than or equal to, because if this is bigger than this one, and this is also bigger than this one, then the combined adding of the two big ones is going to be greater than or equal to the combined adding of the two smaller ones. Now when you add that to that, you get 2k squared plus 3k plus 1. And then I think they've just added a k squared to both sides, and they've got n squared plus nk plus k squared is greater than or equal to 3k squared plus 3k plus 1. Okay, note, my inequality is absolutely the other way round to their inequality, yeah? Now the reason why I think theirs is wrong is because I'm assuming, from the very small amount of work written down here, I'm assuming that they're trying to deduce this from just this fact, from which it's immediately obvious that this fact is true, yeah? Now, to show by counterexample that their statement is wrong, let's take the case where n is 6 and k is 4. Yeah, and I just plucked these two numbers off the top of my head just to see, because I looked at that and I thought, I don't think that's true from that assumption. Yeah, and sure enough, what do we get on the left-hand side? We're going to get on the left-hand side of that inequality, 36 plus 24, well, that's 60, plus 16, that's 76. But on your right-hand side, what are you going to get? 3 times 4 squared, 4 squared 16, so 48, plus 12, that's 60, plus 1, 61, yeah? Now, is 76 less than or equal to 61? No, it's not, yeah? I'm certain they've got that inequality the wrong way round, and I'm pretty sure they were trying, it's probably just a typo, let's not criticise too much. Like, we've all done this. When I wrote questions myself, I made so many little mistakes, and they often weren't, I kind of feel quite often when I'd see the mistakes, oh, well, I didn't mean that. You know what it's like, you think one thing but you write down another. So yeah, let's not be too harsh. I think they were supposed to deduce that. Now, if you look at this, we've got this result, yeah, and then also I argued earlier that n squared plus nk plus k squared must be less than or equal to that, yeah, if that is true. Yeah, and that was from our original assumption that this was a cube number. Basically, if that is a cube number, then n squared plus nk plus k squared must be less than or equal to 2k squared plus 2k plus 1. Oh, but n squared plus nk plus k squared must be greater than or equal to 3k squared plus 3k plus 1. And so we end up with this quite bizarre contradiction. There's a contradiction here, and I'm going to point out at the end why I think they were trying to argue this, but it just looks a little bit different to my answer, because what we've ended up with is that n squared plus nk plus k squared is both greater than or equal to this, but less than or equal to something which is strictly smaller than that. This is impossible, and hence our original assumption is false. So it's a proof by contradiction, essentially. Please do point out in the comments if you think that I've misread their solution, or you think I'm wrong. I'm very happy to discuss this. Perhaps I am wrong. This is impossible, and hence our original assumption is false. I'd be interested to hear your explanation about how they deduced that statement, which is false from that claim anyway. Like, you can't start with that and deduce this. It's just quite clearly false. So yeah, I'll be interested to hear what I'm missing from their answer. I think they've actually made a mistake there in their alternative solution. Their initial solution is very, very clever, and I like that. I really do. It's like, it's a lovely argument. But this works as well, and I think what they meant to do, just to kind of like tidy up what they meant, was they just meant to have this way round, yeah. In which case, when they say for the minimum value, they're basically saying this is true. Like when, in the case where equality holds, you're going to have n equals k plus 1, and if you've got n equals k plus 1 in that, you actually end up with 3k squared plus 3k plus 1 on the left hand side. Can you see that? Because you're going to end up with k squared plus 2k plus 1 plus k squared plus k, so we're now at 2k squared plus 3k plus 1. Let me write it down. We'll end up with k plus 1 squared plus k squared plus k squared. Can you see that here we're going to end up with a 3k squared plus a 3k plus a 1. You're going to end up with the equality case when that's true. So that's the minimum value of the left hand side, but it's also supposed to be what this equals, because remember that equals that, yeah. So if n equals k plus 1, as I argued before, that's going to become 1, and this is going to be equal to this. So you've basically got n squared plus k, nk plus k squared equals 2k squared plus 2k plus 1. Oh, and it also equals 3k squared plus 3k plus 1. And that doesn't make any sense. Have I got it all written down clear down here? Hang on, have I got 3k squared 2k squared plus 2k plus 1. That should say 2k plus 1. Look, see, we all make mistakes. I think we should say 2k plus 1. Yeah. Can you see? Oh, I just want to check that I've basically got the same working as them. Yeah. See what I mean? Like this value, because we're dealing with positive integers, this must be less than that, and yet we've got this is greater than or equal to this expression, and this is less than or equal to this expression. And basically these only hold if k is 0. Yeah. And if k is 0, just to show you that there's a genuine contradiction at the end, if k is 0, we're going to get 1 on the left hand side, and then we're going to get n would have to equal 1, and it's got to be a positive integer k here, not 0. Yeah, and so this is only true. This could only be true. Yeah, I should put that at the end as well. I haven't been quite as precise as I would have liked to have been there. This is impossible unless k equals 0. It would be possible if k is 0, because you get 1 on the right hand side and 1 here basically. If n is 1, k is 0, n is 1. Yeah, so you know, not possible for positive integers k. Okay, so please do let me know if you think I'm on the right track here and they've just made a mistake in their alternative solution, or if you think I've made a big error. Looking at other possible ways to do this, like because the whole question is kind of quite cute really. Well, let's get back to the question. I'd almost like to do it arguing with the final digit. You know, cube numbers, I don't know if you're aware of this, but cubes always end in a number you're cubing. I don't know, like, you know, could you do this by proof by exhaustion? Because all cube numbers, basically, they can end in any of the numbers from 1 to 9. But I don't know, actually, because maybe I'm very, their first answer is very clever. And I would encourage you to remember that way of doing it. I really would, because it's a cool way of doing it. Anyway, I hope that made a bit more sense out of the question. Let me know if you think I'm right, that they have made a blunder there. I think they have just blundered with the typing. It's a typo, and that's it. Okay, all the best and thanks for watching. Bye bye.